So it's good to be back. I missed the conj last year, and I've regretted it for a year, so it's nice to see everyone again. New faces and old faces. I'm going to talk about something I've been working on for a while called Zeta. It's a production rule system, and I'll talk about what that means as an introduction. But the agenda is I'm going to go over some preliminaries, talk about perspective, talk about some complecting and give an overview, and then some ranting and raving. Got to add that in there. And I'm actually going to give a demo, and then talk about what the future holds. So first off, I have to say that I'm very disappointed in the presentation so far, and with Bodil not speaking, we're kind of lacking in many ways, and so I think I'd try to make up for that in the beginning here. So here's a cat, the Wu-Tang cat. Here is a pony. Yes, thank you. I hope I picked the right one. Yes, thank you. I'm not pony savvy, but here's Rich. He's face palming. Some demotivational images. You can look over that for a second. And here's a picture of Elvis with President Nixon. This is one of my favorite pictures, and it sort of brings to mind. I like to start my talks by telling a koan, and I'll tell a koan with this in the background, and I think it'll be appropriate. So, the master and the acolyte were standing together, and the master said to the acolyte, "Why do you never ask me questions?" And the acolyte said, "Well, my previous master, I asked him questions, and he had answers for me about everything." And he said, "Well, really? Well, what did he say?" One day I asked him, "What is the fundamental nature of Buddhism?" And the master says, "Well, what was the answer?" Well, the answer was, "Ping ting comes for fire." And the master says, "Well, that's a very good answer. Do you know what it means?" And he says, "Yes, of course. I think it means that in Ping Ting is the god of fire, and obviously if he would come for fire, it'd be nonsense, so the fire is always within him. Just like us, Buddhism is always within us." And the master said, "I knew it. You didn't understand it at all." He says, "Well, what's wrong with it? What would you say instead?" And the master says, "Well, ask me." He says, "Well, what is the fundamental nature of Buddhism?" And the master says, "Ping Ting comes for fire." And the student was enlightened. So with that in mind, we can move on to, I'll ask a question. What is this? This is a logo. This is the Clojure logo, right? You'd think so, but it's not. It's not at all. It's a lens for viewing computation. So the good kind of lens. We're not going to talk about the other kinds of lenses. So let me give an example of how this is true. One day, Rich looked at databases through his lens, and he had a good idea. Likewise, I looked through the lens at distributed simulation, and also had an idea. And I'll hesitate to say that it was a good idea, but it was an idea. And it's a system called Patagonia, and Patagonia is something I put together for my work, and it really does try to follow Clojure principles. Patagonia was the topic of my other talk submission, and that's the one that was not accepted. So I won't go into this. But let's just say that I found viewing systems through that kind of lens was appropriate, and it was very useful for me. But one thing that I also looked at through that lens were trees, and apple trees specifically. And it really gave me a realization as I was building that system that, in fact, I came up with what I would call Fogus's first law. And the first law is, in the same way that an apple tree apples, so too should your systems tuple. Now, if we have the system Patagonia, and we have information flowing between the nodes, I found something that was extremely useful was to have these things be tuples like datomic tuples. And so whether or not that was a good idea is irrelevant. It was an idea that let me solve a problem, and I felt was a very elegant way. So we do this. I think a lot of people here do this. We look at systems and computation through the lens of closure. And one of the things that we do while doing that is called colloquially decomplecting. Now, if we, as an overview for those of us who don't know, I don't know who that would be, but if you complex something, they would be tangled, they'd be twisted. Decomplecting is a way of pulling these things apart and making them discrete elements that can then be composed more elegantly rather than tangled. So one thing that we can look at through that lens of decomplecting are transients. And so transients, closure transients, are things that provide limited mutability, thread-isolated changes. They're not persistent and they're not references. But what you get out of that by using transients are speed boosts, you would hope anyway. But the thing is that transients complect. It twists up a number of things, and one of them is it has a change policy baked in. It has a sharing policy also. And it has it's sort of a reference policy, I guess you could say, in that it isn't a reference. But by twisting all these things up, you do get the speed, but you also get something that maybe you didn't intend. You were looking for something that was kind of awesome, and you got this. Now, don't get me wrong. I love transients, and I'm not trying to put them down. I'm just saying that if you look at things through that decomplecting lens, that transients are a good exercise, at least. Now, Rich looked at transients through his lens of closure, and he came up with something called pods. Now, pods do decomplect the reference policy and the change policy, and there's a gist floating out that probably is still live that has an early implementation of pods by Rich, and I've looked at that extensively and actually have used it in my system with some minor changes, and the pods in Zeta also decomplect the sharing policy. Pods are a reference type. They allow you to specify a certain kind of change policy. And a certain kind of sharing policy. And as an overview, pods, to integrate with pods, you extend some protocols, of course. And when you're writing into a pod, it goes through this, makes a transient. You always start with an immutable type, and you send it into the pod, and it becomes a transient thing. There's a shareability check. Can it be shared? The really base check here would be, is it happening within the same thread? If it's not, then maybe we want to throw exception. Maybe not, I don't know. But that eventually becomes a value inside of the pod, and when a reader comes along, a shareability check is once again performed, and a value, and an actual value rather than when a transient thing comes out. So that's kind of nice. I mean, I've found them to be extremely nice. But it leads me into some ranting. Now, decomplecting is extremely nice, and I think that in the closure community, we tend to follow a policy of making small libraries and providing them publicly so that people can take sort of a la carte and mix these libraries together. But recently, I've been kind of down on that because what I've found is that while at the core, our libraries are built to be easily composable, really they tend to be built just because they're easy to build. And they don't really integrate as well as they could. And one of the things that I have found is that it doesn't happen much in closure, but I think that it's becoming more prevalent, is that people are starting to make more and more libraries that offer functionality that is almost exactly the same, but slightly different here and there. But it's a minor rant. It's not a big deal. But it did lead me to another realization, which I like to call Focus's 10th rule. And I'll let you guys read this. I won't read it. But I've found that many systems out there are implementing partially a production rule system. Now, the one that I happen to pick for the rule is OPS5, which is one of the earliest production rule systems, if not the earliest. It was invented in the 70s, as all good things were, myself included, by Charles Forgy. It's an implementation of something called the Reedy algorithm, which I won't really go into for this talk, maybe in a future talk. But it happens to be incredibly efficient for matching over largest data sets. And it was initially used to implement an expert system that was a system configurator, I believe, for VMS, but I might be saying that wrong. Maybe someone can correct me later. If you want to know more about OPS5, you can check out these books. I was talking to Brenton Ashworth yesterday, and he said to me that he's very angry at me because when I recommend a book to him, he winds up reading it and hating it. So buyer beware, but these can probably be had for about a penny on Amazon. So to give just a slight overview of OPS5 and how it fits into this talk is that, now let's say you have a piece of code and you're using Datomic. So up at the top there you have your schema, elated, of course, and a function that just takes a username and generates a salt and stores the username and the salt in the database. Now something along the line triggers a call to that function, and it might be, say, a composure route or something like that. You know, you've got a request and you're performing this action on the back end. And OPS5, an analogous piece of code for that is, at the top again, you have your schema. But the way that the relationship between a username and a salt is described happens differently. And that happens as a production, and a production can be viewed as there's some data in the system, and it matches some form. And when there is a data that matches, this arrow says that this is the thing that should happen when a piece of data matches. And what happens is when we have a username with no salt attached in our production, our knowledge base, we want to go ahead and add a salt. And don't use this salt in production, please. This is my salt. And the thing that triggers it is really just the addition of some knowledge to the knowledge base. The production will match automatically. And that's what the Reedy algorithm took care of. It made that kind of match extremely efficient, even in the presence of growing data. Now, speaking of decomplecting, going back just a moment to talk about that, there's a paper out there called Out of the Tar Pit. And I'm sure, raise your hand if you've read this paper. I mean, I'm sure a lot of people here have. I highly recommend the paper. It is, in fact, I would say, the Decomplector's Manifesto, if such a thing exists. And it describes a way of interacting with a system via, by storing things as relational data and then performing relational queries over the data and figuring out the way the shape of the system. Not to libel the paper. I mean, it's obviously much deeper than that. There's things like feeders and observers and all this really cool stuff that you could spend a year reading it and trying to figure it out. But there is one problem with the paper, and the problem is that they don't really have a good story for how to describe data change within the system. And there's not really a language for that as described in the paper. And I really think, having thought about it for a while, I think that one way of maybe approaching that shortfall of the paper is to use a production rule system as a way of describing the way the data should change shape over time. And so what I did is I said, I thought about decomplecting. I thought, well, maybe there's a better approach than decomplecting to get there, and that's recomplecting. So recomplecting is, you think about Legos, and you have these one-pip Legos, and they're very versatile, and they can perform almost any task that a Lego model builder would want to do, except that they are not really appropriate for every task. I mean, if you're trying to build an arch over a door, you wouldn't want these one-pip Legos. You would need other things. And so you could build many structures with the one-pips, but it might be more appropriate to have larger structures to build your Lego models out of. Taking that a little bit further, Rich, if you listen to Rich and Stu talk about Datomic, they'll talk about how you take they're helping to enable putting brains into your application. And so you have, instead of relying on a big server to perform your queries for you, your query capability is right in the system. And while I think that is brain-like, you're still sort of losing some of the relationship between data and the behaviors that act on it by taking sort of a functional programming approach and splitting up your design space over an area of many functions. So rather than being brains, it's sort of a bucket of neurons, right? I mean, it's we have our data and our function, and in between, the way that they meld is via behavior. It is called behavior, and the behavior. If you think about it another way, data is a tactical thing, and functions are tactical. Behavior is strategic. This is the things you're actually trying to accomplish. Data and function are somewhat merged in those two things. And there's a good quote I kind of like, and it is very appropriate for the way that production rule systems work. And it's by a chess player, an older chess player, and he says that tactics is knowing what to do when there's something to do, and strategy is knowing what to do when there's nothing to do. And I'll try to illuminate that a little bit more as I go, especially when I give a demonstration of the capabilities. So as an overview, this is what Zeta looks like. This is not an up-to-date image because I don't show inner queues and all kinds of stuff, and function call names are slightly different now. But this is basically how it looks. You have the meat of it up here in this box, and the box is called an engine. And you have your facts and your rules and your working memory. You can watch that stuff, and the stuff that coming out of the right side there is the specification of the system. So when you dereference one of these things, you're going to get out effectively a snapshot of what the system looks like at that moment. So that's mostly accurate, and it can hook into Datomic, which I'll actually show. You can query the Datomic, you can query the engine. So some of the reasons that I made Zeta is that I'll talk about now. So the driving principles are, I really actually just needed to do something. One of the things I needed to do was to build sort of intelligent systems that simulate experts interacting. Say, you have a bunch of experts in a room and they're drawing stuff on a whiteboard, and they're augmenting each other's as knowledge. So the interaction between the experts is more powerful than any of the experts by themselves. So I use Zeta as creating expert systems that live within that Patagonia system and provide services and model behaviors. Another driving principle is that data is awesome. I don't have to say that to you guys. I mean, you guys know that, right? I mean, I did want it to be a data-driven system. I want it to be fully described via data. And if you read the second edition of Joy of Clojure, we talk about data programmable engines. And so this is sort of follows that model where you feed data in and something happens as a result of that data. It's pseudo interpretation, I guess, but everything is driven by data. I didn't want to invent anything, so nothing that you'll see here is novel. It's actually looking at systems via that lens that I talked about, and sort of taking some good ideas and trying to put them together to solve some problems. Protocol orientation, I really won't get into that very much. Time constraints, and it's sort of an evolving thing even today. But I've rewritten the core of the engine multiple times, and they've all adhered to this sort of protocol, and they're swappable, and I've really found by leveraging the protocol, focusing on protocols, I was able to really get a lot of power out of that. Pattern matching. So one thing that you'll see in production systems is that very often they have a pattern matching language, and I wanted to adhere to that as well. You'll see that in a moment, but the thing that I like about the pattern matching is that you have a piece of data, and you can sort of draw a sketch of the kind of data that you want, and the engine will go out and retrieve that kind of data for you and perform actions based on that. I want it to be a library. One of the nice things about Clojure and Lisp in general is that you can get extremely powerful capabilities just by making it a library. So, and immutability, of course. I mean, I wanted things to be by thinking immutably from the beginning. I think that I was able to really come to a neat system. We try to follow that. I try to follow the principle of immutability. It's not always 100% possible, and in Zeta it wasn't, but there's an appearance of mutability, which is just as good, I suppose, from an outsider's perspective. And it should be fast, and it is fast, and I've been benchmarking it over time, and I think for a lot of tasks that you can solve with something like CoreLogic, it doesn't solve the same kind of task always. You can have an intersection between the types of tasks you can solve with CoreLogic, but it's comparable with CoreLogic speed, so I'm very happy with that. So yeah, let me give it a demo. Let's see what it looks like. So I need to switch my screen around. Is that it? That's it. Oh boy, that's smaller than I thought. But anyway, we'll work it out. I'll do some selective highlighting along the way. So to use Zeta, you just pull it in like you would any library, and Zeta schemas look very much like a datomic schema. So you can see, you have your identifier, you have your type of the data that you would that you want your relation to be. There's a cardinality, and this was making it look datomic-like was by design, because I wanted to leverage a lot of the same schemas that I was already using. And so while it's a work in progress at the moment, I can take these Zeta schemas and transform them into datomic schemas and populate a datomic database along the same way. And as you see, there's no docstring like all good libraries. So let me talk about this. So this is called a fave schema, which is just a way of saying there's a favorite food. Someone has a favorite food, and it's of a type keyword. There's only one. You can only have one favorite food. This is sort of the datomic example. The pizza. People like pizza, right? And this is another relation type, and it's a hungry relation. So it's a type Boolean. And it just says, is the person hungry? They can either be hungry or not, so it's just the cardinality of one, no docstring. And a plan schema. The plan schema is, what does a person plan to eat? It's of type keyword, and we'll see how that works out. The cardinality is again 1. But the really interesting thing are these things called rules, and they look very similar to the ops5 rule. they have a left-hand side, which are the things that are matching. So you have things that look like tuples, and one of the ways I was able to get a lot of speed out of the system is by making an assumption of the way that the data is shaped. So I don't allow arbitrary data. I allow tuples, like a datomic datum. So you have a thing, you have a person that this logic variable gets bound to some person ID. Their favorite food is bound to some favorite. It's pretty straightforward, especially if you've seen datomic, you probably know this. Now this is a constant here, so it says when the person hungry value for the same ID is true, then we want to do this thing. And what this thing down here is, it says all rules return a sequence of things, and what this is returning is a vector, a sequence of tuples, but only one tuple. And so if a person has a favorite food and they are hungry, then there's going to be a new tuple inserted into the Zeta system that says they plan to eat that favorite food. So that's all that says. For that ID, there's a favorite, and that's the thing they plan to eat. You'll see other things that you can put into this sequence that gets returned from the production rule, but for now that's pretty good, right? I mean, we'll get into that other stuff later. So the data that goes into it is just these tuples, like I said. This is a nice little convenience tag literal that I created that I'll talk about in a couple minutes. So the seed data that goes into this is just for one person. A person's favorite food is nabe, and I don't know if you've ever had nabe, but it's fantastic. I suspect Yoko did. I saw her over there. You've had nabe. So meal plan. So this is the Zeta engine, and so I was talking to Rich the other night at dinner, and he said that he's looked at production rules often, and he likes them, but he's never used them. So I think that's kind of a story that I hear a lot, and I think one of the reasons is because very often production systems are holistic, and they say you have to do things a certain way. So if you want to use this production system, it's all or nothing. That's not true for all production systems. I just want to say that is a characteristic of many. So what I'm trying to do here is this is a library, and the production system itself is just a reference type, a new reference type called an engine. So you feed in the schemas that I described above, any rules, and any facts. You can supply any number of these things and populate them as you go if you want. So to look at it, a meal plan it's dead. Okay. Oh, I know why. I like when it happens. I didn't evaluate it. So now we have a meal plan. We go ahead and get a snapshot of that, and it's the current state of that engine. So it has some rules attached to it. It has some data, and we can take that snapshot that we got of that engine, and we can populate another engine. I'm not going to show that because it's not entirely interesting just showing it, but maybe another day I'll talk about how that's done. But one thing to look at is, and the screen doesn't show up, but that's okay, we'll get into that later. So queries are just that datum structure. It can contain logic variables and they can contain constants. So here's one thing that we can do is we can query using the same type of shape as the rules themselves. And one thing that I really miss about using datomic is that I'm constantly querying it and getting data out of it and doing something with the data, and then putting it back into the database. So this is sort of this is recomplecting those three stages. We want to use the same. We want to use the query as a way of triggering behaviors. So this is a query called all favorite food, and we don't care what the ID of the person is. We just want to know that they have a favorite food. So if we go ahead and evaluate that, and then we query off of a snapshot of the database, And we get the one thing, the one person who likes nabe. So that's nothing really all that interesting about that. But we can also have parametered queries, which is somewhat analogous to datomic rules, but it doesn't work quite the same. And although this query language looks like Datalog, it's not recursive. So Rich, if you were going to ask that question, the answer is no, it's not Datalog. I intentionally did not make it recursive because it confused me too much. So this is a specific favorite food, and it takes an argument, and you can pass in a specific favorite food. And that argument that's passed in becomes the target value on the match. So there's a favorite food, and it should match that specific food that was passed in. So when you do a query, you can pass in the arguments at the end. And yes, of course, there is that one person again. But what about, we can ask, does anyone like natto? And of course, no one does. Who would? Sorry, I'm sorry if you like natto. So yeah, what about assertions? What if we want to put data into besides just seeding it, we can seed it in the beginning, but as a system runs, we want to put data into it. So again, it's an ID, a keyword, a value, an entity, attribute, value, if you want to think about it that way. We can generate IDs. I use UUIDs as the ID field, but you can use anything that can compare with another thing. Just doing a gen ID will return a UUID. It's not all that interesting, but this is kind of cool. One thing I found in Datomic that I just created something like this that would do the right thing, but is that keeping same IDs among related datums was a little bit cumbersome. I just added this little thing in there, and then now it works. And so I don't know what it's like now, so maybe it's different. But these tag literals, you can put a tag in there, and it'll give you something called a cursor, which is just a way of taking within a single transaction, all of the things with same tags will get the same ID. And if it's an underscore, then it'll just get any ID. It doesn't really matter. And you'll see how that works. So, to create a fact, you just create a vector of the stuff that you're looking at. So here's a fact that says, there's some person out there whose favorite food are Tic Tacs. And to put that into the database, you make an assertion, which is just the same thing, that same tuple, a sequence of tuples goes in, and a new version comes back out, a new version of the engine comes back out. Now, of course, it's in that pod-like structure, so the pod itself is updated. But you do get that new version out if you need it. So to do a query, we check, is there someone that likes Tic Tacs? Of course there are. And it's data. It's data as you would expect. It's just a vector, and so you can pull it apart. And then let's say you want to say that person who likes Tic Tacs. I hope this is easy to see. It looks a little bit jacked up, but we'll have to work with this. So you want to say you grab that ID of the person that matches that query. That'll fail if I don't do this. There we go. And now you make an assertion, and now there's a person who likes Tic Tacs who's hungry. So one thing that you couldn't see on that is that there was a part of that returned engine that said fires, and fires are the number of rule activations that occur based on some data being put into the engine. So we can have a new query that's called hungry, and if you have kids, you use words like hungry. So hungry is we do that, and there's a couple people who are hungry, one who likes Tic Tacs and one who likes nabe. And there's a little convenience function that just takes the tuples. So every query that happens against Zeta returns just the raw tuples. And this is just a way of tying it back together into a map. It's sort of like an entity thing, but not as awesome. So you recall the rule for the planned lunch was that there's a favorite food, a person was hungry, and when that person is hungry, you create a plan. So now that we're going to make that person who like nabe hungry, and so they're going to fire, and we can't see that, of course, but just I assure you that they have a plan for lunch, and we'll show that by going to all plans and doing the tuple map, and favorite food, the Tic Tacs. They're hungry, true, and they have a plan to eat, but you can't see that. But it looks like this. They have a favorite food, Tic Tacs. The same person is hungry. They plan to eat nabe. That's not right. They plan to eat Tic Tacs. This person, nabe, true, plan to eat nabe. So, so we'll look at that. All the plans, nabe, Tic Tacs. Okay. So that's a real high-level overview of what it looks like. There's a couple of cool features, and I don't have a lot of time, but so I'll sort of buzz through those. One thing that is kind of cool is that Zeta allows negation. So there's relationships between data, fundamental relationships between data, and one would be, in that previous model, if a person's hungry, they want to eat something, and so using those rules, we can make that association between the fundamental association. But there's also an association between certain types of data and the non-existence of data. And so what Zeta allows is describing that kind of relationship. So we have a schema. There's a username. It's a type string. There's one. And there's a salt. This is sort of like the ops5 example. It's also a string, and there's one. So the rule is called detect unsalted user. That's very difficult to see. And there's the doc string. I finally put one of those in. So there's a user. They have a username. And the user, via this fancy metadata, says they do not have a salt. So if we put, you would think if we put a user into there with a username, we would want a salt. So that's what that says. If we have a username with no salt, go ahead and assert that there's a salt. So we want to partially populate by saying, let's go ahead and put a user in there with just a name. And of course, I did the wrong thing again. Okay, now we got our stuff. Go ahead and assert that. We get a new version of the database. We go ahead and create a query that looks up all the usernames. There's just one, Fogus. We go ahead and create a query that looks up all the salts. We go ahead and look, and there is a salt in there now because of that rule that said that when that a relationship does not currently exist, we were going to make it exist. I'm going to skip over spreads because I think we can get that later. Datomic integration. This has proved kind of useful, although it's not as nice as I would like it to be yet. But we have a Datomic database out there somewhere. We go ahead and I've created it and gotten a connection to it and defined some schemas. And this is just a description of the unsession. So there's an unsession that has a title and a description and a tag. The tags are enumerated types. And there's another thing that says, am I interested? Am I interested in it? So there's a Boolean out there in the database that says, I am indeed interested in that unsession. And these are the tags. There's a tag core async and Hadoop and music. And I've gone ahead and put the schema into the database and added some data, which are some unsessions, the core async unsession and the Clojure and Hadoop unsession and the backends of ClojureScript core async. So I've also created an engine that has similar data, similar schema of data, except it only tracks tags, and it only tracks tags, and it tracks interest, which is a Boolean. Am I interested or am I not interested? And, oh boy. So the way to get at the Datomic database is to define something called a tap. And a tap is defined basically just as a query over the transaction report log. And so this is probably the most useful of queries for integrating with Zeta, and it basically just says, based on a certain tag that you're interested in, go ahead and pull up the values for that tag, and the the entity attribute value tuple and go ahead and populate it in. So all I'm really interested in tying it together is the tag key. So if I go ahead and add the data into the Datomic database, I've set up the tap, and I query the Datomic database. I go ahead and I see that there's some tags in there, core async. But then I also query the Zeta database. Those tags are also in there. And additionally, if I add new stuff into the Datomic database, it automatically shows up in the Zeta database. Now if I want to look at the schedule for Zeta, that Zeta has built, I can go ahead and do that. And you can see I say I'm only interested in the core async stuff. So there's a lot more to show. I wish I had a little bit more time, but there's more to say about this. And one is, it's not just a way of doing data rewrites. So right now I've really only showed using Zeta as a rewrite engine, but you can do arbitrary computation, and I do that in one of my examples that I couldn't get to, but it was a block sort implementation. So there's this classic AI program that says here's a pile of blocks, here's a pile of blocks. The goal is I want to put some block over in this pile on top of another block in another pile, and it does that all via rules. And I can show you that after if you're interested during lunch. So yeah, that's all I have. This is an ongoing project, and I hope that I have more to show in the future. Thank you.